Welcome to Engineering Studios. Global warming, climate change, decarbonizing, net zero, carbon neutral. You must have listened to those words very often from different sources, if not all, at least one or two. What do they exactly mean? And how do we link those to the engineering practice? Let's figure it out from this video together. You probably check the weather every morning to see if it is lovely weather to take a walk. Or, you may worry about the weather next week and check the weather forecast and see if it is good to carry on with the plan of traveling with family or friends. However, not many of us will check the climate change. As compared with the weather, the climate is referring to a much wider geospatial space and a much longer time scale. It may not be significantly noticed in our day-by-day life, till the point when our living space gets threatened. So, how the climate has changed in the past. Let's see a few facts that have been observed and captured. The Arctic sea ice extent drops about 13% per decade since 1979. The global average sea level has risen about 10.2 centimeters since 1993, and nearly 18 centimeters over the past 100 years. The ocean heat has added about 337 zetajoules since 1955. The past 20 years has seen the warmest ocean temperatures on record. Global temperature has risen by 1.01 degrees Celsius since 1880. Global warming is a confirmed trend, which is observed and supported by heaps of research. But what is the reason for this change? The sun is definitely the source of our energy. Can we blame the sun for global warming? Since 1978, a series of satellite instruments have measured the energy output of the sun directly. The satellite data show a very slight drop in solar radiance over this time period. Hence, the sun doesn't appear to be the reason. Further studies show that this trend is actually the result of the greenhouse effect. The solar energy reaching the Earth's surface is absorbed and then radiated upward in the form of infrared heat. About 90% of this heat is then absorbed by the greenhouse gases and radiated back toward the surface. Certain gases in the atmosphere block heat from escaping. Gases that contribute to the greenhouse effect include carbon dioxide, methane, nitrous oxide, hydrofluorocarbons, perfluorocarbons, and sulfur hexafluoride. While carbon dioxide is recognized as the most important anthropogenic greenhouse gas. To ease the measurement the greenhouse gas effect, carbon dioxide equivalent is introduced to be the unit of measurement. It allows different greenhouse gases to be compared on a like-for-like basis, relative to 1 unit of carbon dioxide. Till this point, you must have figured out. To slow down the global warming process, we must reduce the discharge of greenhouse gases.
Many countries have set up the goal of net zero by 2050, which means the greenhouse gases going into the atmosphere are balanced by removal out of the atmosphere. Under this circumstance, what is our position as engineers in this transition period? According to the relevant data, the carbon dioxide emissions from manufacturing industries and construction could take up about 20% of all carbon dioxide emissions in general. This is the place where engineers can influence reducing greenhouse gases emissions. In our another video, Life Cycle of Structures, the whole life of a structure is accompanied by the engineer's input. When we come up with the engineering solutions, the carbon emission could be accounted for. So, the question comes, how could we assess the carbon emission in structural engineering quantitatively? It has been well accepted that there are two measures of carbon emissions, carbon footprint, and embedded carbon emissions. A carbon footprint is the total greenhouse gas emissions caused directly and indirectly by an individual, organization, event or product, and is expressed as a carbon dioxide equivalent. Embedded carbon emissions are the subset of a carbon footprint, and can be treated as the carbon footprint of materials. Embedded carbon emissions are caused by greenhouse gases from non-renewable energy sources, or otherwise being released into the atmosphere due to activities associated with a particular material or product. All the structures are built using the construction materials, steel, concrete, timber, etc. The embedded carbon is a measurement for sure, but is that enough? If we look closer in structural engineering, there are transport structures and buildings as subcategories. In the buildings, the operational carbon is quite significant as the result of human activities within it. Hence, the carbon footprint should be used to cover the wider carbon emissions in buildings. While in the transport structures, embedded carbon emissions can predominantly measure its whole-of-life carbon footprint. The calculation of carbon dioxide equivalent is a specialized topic, while its meaning is straightforward. From a decision-making perspective, the carbon emission is measured from the whole-of-life operation of the structure, then it will be taken into account along with other factors. To standardize the carbon emission calculation, some governments have released their carbon emission factors through the official document. Those documents are open to the public, encouraging their utilization. From the structural engineering industry, here is the unit weight of construction materials, energy and waste with their corresponding carbon emissions. This is based on the New Zealand standard. To produce 1 kg of steel, the carbon emission is 2.85 kg carbon dioxide equivalent. To make the same unit of concrete, it is 0.203 kg. To produce 1 kg of timber material, carbon emission is 0.015 kg. Purely from the material perspective, timber is more merit than others. But remember, the best solution is tested on its whole life basis. And the carbon emission is one among other decision-making factors. From the energy point of view, burning 1 liter heavy fuel oil will generate 3.22 kg carbon dioxide equivalent. Burning diesel, it is 2.69 kg. Using 1 kWh of electricity, the carbon emission is 0.0977 kg carbon dioxide equivalent. Using these carbon emission factors to calculate the carbon emission of cars, by driving the same distance, the electrical car has much lower carbon emission than a fossil fuel car. So it is not hard to understand why we are promoting electrical cars in the transition period, towards the net zero goal in 2050. The last but not least, from the construction waste treatment point of view, 1 kg construction waste treatment will generate 0.14 kg carbon dioxide equivalent. Now with carbon emission factors known for material, energy and waste treatment, engineers can calculate the carbon emission of different solutions. The carbon emission calculation is based on the well understanding of the whole of life stages of a structure, and its corresponding engineering activities. We should always bear in mind that, the carbon emission will join other factors in decision making. The weight contribution of carbon emission compared with other factors is a case-by-case approach.
Now, we can roll back to answer the beginning questions. Climate change is the challenge we have observed. It is reflected as the threat of global warming. Decarbonizing is the action we slow down global warming, with the goal of carbon neutral, or net zero in other words. Down to structural engineering, we will use quantitative tools to measure the carbon emission of different engineering solutions, which is carbon footprint and embedded carbon emission. The outcome of the quantitative carbon emission calculation will be accounted in decision-making with other factors. That is all for this video. Thanks for watching. Subscribe to keep updated. See you next time.